Hello everyone. In our previous lectures, we have seen how to do efficient addition and we have seen multiple ways of doing it. And from those additions, we have learned some new design techniques also. Today, we will extend that idea. We'll see how multiplication can be done using logic gates or using Boolean logic or a digital logic. So, in this lecture, we will focus on multiplication as well as what are the issues in a regular or in a naive multiplication, how we can make it faster. So, when we are discussing techniques how to make it faster, then we can also see some new design techniques. Okay, so a regular classical multiplication is essentially a two-step process. First, multiplicand is multiplied with each bit of multiplier and each partial product is shifted by one place. So this way we got a series of partial products and finally those partial products are added. So we can say there are two steps: one, generation of partial products, and then second one is addition of partial product. While generating partial products, let's see this example of 4 cross 4 multiplication. So each partial product is shifted by one place. So the shifting essentially means that to which place of multiplier we are multiplying with. So now multiplier, if we are multiplying with the 0th bit, so that means the partial product is at the original place, but when we are shifting, when multiplier is at 2's place, then the partial product is shifted by one place towards the left. So similarly, when we are multiplying with this one, then the partial product is shifted by two places towards the left. So this way all the partial products are obtained, and then finally we add all of them. Now if we use a simple addition, then we also see that the total number of bits in this multiplication process, it is like proven that if the multiplicand is n bit and multiplier is m bit, the total bits in the sum would be n plus m bits. So this n plus m bits are sufficient to represent any result. For example, if my multiplicand is 32 bit, multiplier is 32 bit, the total result would be 64 bit. Will never be more than that. So to do this multiplication using digital design or digital logic, so the way we can do is we can, as we have discussed in our previous lecture, so we can do addition of two partial product, and then whatever is the sum, then we can add that to the third partial product, and then we can add it to the fourth partial product, so on and so forth. So total number of m minus 1 adders would be required, and in the worst case the size of each adder would be n plus m. In average case it could be little less by properly sizing it. So for example, first addition we can say that the size could be 4 plus 5, 5 bit addition can be done, then 6 bit addition, then 7 bit addition, so on and so forth. But yes, the cost looks huge in worst case, as well as if we try to reduce it by proper sizing, then also it is substantially large. So how to make it better, because multiplier is like addition, multiplier is also a fundamental unit used in almost all kind of designs. For example, when we write C program, we never think twice whenever we need to do multiplication. Okay, so we consider that as a cheap operation. Cheap means that it's probably will consume less time, less area. But yes, looking at this, it looks like that my multiplication is going to be at least one order. If it is n bit multiplication, it's going to be at least n times more costlier than addition. So how can we do better? So in our last lecture we have seen carry save adders. Can we use that? Probably that looks like a very wonderful idea, because in carry save adders multiple operands were there, and we were adding those multiple operands, and we were doing this carry save thing, and carry propagation was done only in the last stage. But in our last lecture when we were studying about carry save adders, so this carry save adders looks like a special case, and also each time we were doing some like combinations were created in a special way, so in an ad hoc way. So can we do it in a more systematic manner? So let's try to see this with an example of 8 cross 8 multiplication. So in an 8 cross 8 multiplication, this carry save adder will work only in the second step. In the first step, where we are generating partial products, carry save adder is not going to help there. But once partial products has been generated, after that it can help in addition, fast addition of all of them. Now let us say we are doing 8 cross 8 multiplication, and each of these dot represent one bit of the partial product. So this first row represent first partial product. So because it's 8 cross 8 bit, each bit would be so each bit of my multiplier would be multiplied with the multiplicand. So these 8 bits, I'll receive these 8 bits. Similarly, when the second bit of multiplier would be multiplied with multiplicand, then this row would be obtained. So similarly, I would have such 8 rows, and each of these 8 rows represent my 8 partial products. Now I need to add all of them. To add all of them, and also I would like to use carry save adders. So to use carry save adder, what should I do? I have to identify that which bits I can add in parallel. So we see that here these two bits are actually of same order or same power, or denotes same place, so we can add both of them. And similarly, these three can be added because they again belong to the same place. So similarly, all these three can be added together. Okay, so like this we can also add all these 3 bits in this particular these 3 rows, and these we are leaving because the fundamental method is the fundamental method which we are using to create these groups is that if number of rows or number of dots, number of wires I can say, are more than, let's say, multiple of 3, then I can make group of 3. So but if it is more than 3, more than, let's say, for example, here it is 8, so we are leaving these 2 so that we can use them in later steps. Okay, so this way we are creating all the groups, and the groups are created based on equal powers. Now after doing this grouping, now each of them, this would require an half adder, this would require an half adder, and these bits would require some full adders. Similarly, these bits would require full adders, so all of them would be added, and every stage these 3 would be now for example, for this addition I will generate carry and a sum would be for this place and carry would be for this place. Okay, so this way what we can see that if we see the result of this first stage, let's call it a stage. So in the first stage we have grouped these many groups, and the result of this group would be this stage. So for example, there were 2 dots here. Now this is the sum, this is the carry part would be in the next group. So similarly for all others, now there were 3 bits here, so these 3 bits converted into 2 bits. So this way, this is the result of stage 1, where we are able to eliminate these dots. So essentially what a carry save adder is doing for us, that it is removing. So instead of adding 3 numbers, now it will reduce them to 2 numbers, sum and carry, while carry would be in the next order and sum would be in the same order. Okay, so let's try to see it closely enough. We'll keep flipping this slide from previous slide to this slides to understand how this step has been done. So you see that there were 3 bits here. So these 3 bits, the sum would be here and the carry would be in the next group. So sum is here and carry is here. So similarly for this group, sum would be here and carry would be shifted to the next place. So sum would be here, carry would be shifted to this place. So to make things easier, we have shown in two different rows, but essentially they were all belonging to the same row. The only thing we have to understand is that each of this full adder will return sum and carry. Sum would be would result in the same column, but carry would be given to the next column. Okay, so similarly for these also, the sum would be here and carry is here. Sum is here, carry is here. So 1 2 3 4 1 2 3 4, so total 8 1 2 3 4, so total 8 additions were there. Because of those additions, we are essentially able to eliminate one whole row. So we are able to eliminate this row, we are able to eliminate this row. So after one stage of addition, instead of 8 rows, now we have 6 rows. Okay, so now we can reorganize this result. So for example, we can shift this dot from here to here, we can shift this dot from here to here. So if we will reorganize, it looks something like this. So we'll have total of 6 rows, and now again we can go ahead and group them. So we can find out in this stage 2, after rearranging, how we can do additions. So we can group these 2, we can group these 3. So you will see that we are able to do some 8 additions here. The same 8 additions we can do here also. So we are leaving wherever single dots are there, because they can be added in the next stages. So again, after doing this addition, total number of rows would reduce from here. The number of rows are 6, so these 6 rows would reduce to 4 rows essentially. So we have removed all of them. Similarly, this particular row is eliminated. Now this dot we can move upside. So if we rearrange them, after rearranging, so after rearranging, this will become 4 rows. Now this is the result of stage 2. After this stage 2, again we can reapply our carry save additions. In this carry save addition, we can again form this is the group of 2, this is the group of 2, this is the group of 2, and now these are the groups of 3. So these additions we can go ahead and perform, and after this addition, now these 4 rows would be reduced to 3 rows. Okay, and these 3 rows again we can rearrange so that we can perform the addition again. So what you are observing, that there are multiple stages, we are doing multiple additions, and after each addition some rows are getting eliminated. Okay, so after this stage 4, again we can go ahead and perform these additions. We can form wherever we can form groups. So after forming additions, like now these 3 rows has been converted into 2 rows. This is the result of stage 4. So after stage 4, now this is essentially the last stage. In this last stage, what we had to do, we will not use carry save adder, but propagation has to be done. So each time, so for example, addition of these 2 bits would be giving carry to this addition, and similarly addition of this carry, addition of these 3 bits would be given as an input to this addition. So essentially carry would propagate now. So in this last stage, it's a carry propagate adder. Okay, so the design of adder would be like a propagating carry, where every stage, every set of bits would be giving input in the next set of bits. So now the delay of this 5th stage is essentially equal to a carry propagate propagate adder. Now if we see the overall delay, so because before these there were 4 stages. All of these 4 stages were consuming 1 adder delay. The worst case was 1 adder delay. The total amount of delay I can say here would be essentially equal to approximately order of n. So because of the previous 4 stages, now I need not to do any kind of addition for these 4 bits. For rest of the bits, yes, I need to do addition. So if 8 cross 8 multiplication is resulting in 16 bits, so I would require this addition 12 full adder additions here, and the 4 additions has been done in 4 different stages. So the total delay is of the order of n, or basically n plus m. So if I have a multiplier which has multiplicand of size n and multiplicand of size m, so the total delay is going to be n plus m, of the order of n plus m. Correct? So what would be the impact of number of adders? Number of adders would also reduce substantially, because we are playing smart here. Wherever number of bits are sufficient, then we are adding, otherwise we are not adding. We are also leaving it to the next stages so that we will have a sufficient number of bits which can be combined together. So this forms a very efficient technique of multiplication. This is called Wallace tree multiplier. So in this Wallace tree multiplier, the group of additions are created in such a way that the number of stages are less. What are the number of stages? The number of stages are approximately log n. Okay. So how do you come to this factor of log n? Because after every stage, ideally we should be able to remove or basically reduce the number of rows into 2 by 3. After every stage, because the number of stages are reduced to 2 by 3, so if my addition is very, very large, so the number of bits are very, very large, so the number of stages would be log of the order of log n. And then finally in the last stage we are going to add them in a carry propagate manner. So the delay is always going to be of the order of n full adders. Okay, so this looks good, but there are still some challenges or some issues in this Wallace tree multiplier or multipliers like them. So first, the issue is that you have a very irregular structure. So if you have seen that every time you require to do addition, so you don't know. So basically you have to lay out, you have to fix all these bits, and you should know in every addition that which particular bit you would like to connect to. So you would require n number of adders, different number of adders in every stage, and every stage would require different kind of interconnect also. So it's not very regular. It's not that one bit is always going to the next adder. So the overall technique is not said to be layout friendly. Layout friendly means that it's not rectangular in nature. So in some particular stages number of adders are more, in some other adders are less. So to this irregularity problem and layout issues and irregular interconnect issues, some people have provided a different kind of tree structures. Like in Wallace tree, the structure is different. There are other trees where the structure is more uniform, so that the number of additions could also be minimized. Number of full adders requirement can also be minimized. People have, so this Wallace tree has been proposed some 50 years back. So in last 50 years, people have done a meticulous calculation that which particular creation of which particular group will lead to minimum number of full adders or minimum number of half adders. So with those calculation, number of full adders could be minimized, plus interconnect can also be minimized by creating more a regular structure rather than a haphazard structure where any bit could be added to any other bits. So with those, yes, this Wallace tree are still the kind of fastest multiplier or a tree based multiplier, I would say. These tree based multiplier or carry save adder based multipliers are still the among the fastest multiplier we have. So in any kind of a VLSI design, or a digital design, these three multipliers are going to be the fastest one. Okay, so do we have some other alternatives? Can we make it even more structured or even more systematic, so that it can be done in a more peaceful manner? So for that, let's try to understand one more multiplier, which is called an array multiplier, or it's also called combinational multiplier. So here, the beauty of this method is it's not saying that give me the partial products, then I will add. So it has combined the generation of partial product as well as summation. So each row is essentially doing the partial product computation as well as doing the multiplication. Okay, so let's try to understand this particular multiplier with a 5 cross 5 multiplication example. So and the example is generic enough that you can easily extend it to any kind of multiplication. So we are considering 5-bit input x and 5-bit input a. So this x is x0, x1, x2, x3, x4. Similarly, a is a0, a1, a2, a3, a4. Now this x is being multiplied with a, so my multiplier is x, and a is my multiplicand. Now since x is my multiplier, a is my multiplicand, so in the first stage, here also I am trying to use the same word stage, but the meaning is slightly different here. So in the first stage, I am adding two partial products. So a0, x0, I am doing an AND gate, and x0, a1, x0, a2, x0, a3, x0, a4. So this is the first partial product. The second partial product is x1, a0, x1, a1, x1, a2, x1, a3. Where is x1, a4? It would come later. Let's see. So we are using these 4 full adders. So this is a full adder, this is one operand, this is the second operand, and carry is 0 here. So carry is 0, and we all know that in whenever we add this first stage, x0, a0 will always form the first bit of the product. So there is no doubt about that. So we can simply keep x0, a0 as p0, and since addition of these two is also there, x1 a0 and x0 a1, addition of these two will also result in p1. So this is also pretty clear. So but for other additions, for other results, p2, p3, p4, etc., we need to add more. So here, using one layer of addition, we are able to add two partial product that results because of x0, the partial product that results because of x1. These two has been added using one row or one layer of my full adder. Now similarly, the result of this full adder layer, there would be two results. One would be sum, another would be carry. Now I can add this sum and carry to another layer where the third input is coming from the third partial product. Third partial product means multiplication of x2 with my multiplicand, x2 a0, x2 a1, x2 a2, x2 a3. So you remember in our previous layer, x1 a4 was missing. So this x1 a4 was just left like this, and this x1 a4 is added to the adder in this new layer, in the second layer. So in the second layer also we'll have we are adding the result of previous partial addition. We have done the partial addition, and the result of partial addition is now added to the new partial product. So this partial addition, you see the carry is also generated after every addition. So that's why we are using full adders here. So whatever is the carry from this adder is added as a carry here. Whatever is the result of carry here, that is added to the carry input of that is connected to the carry input of this particular adder, full adder. Similarly, a result of this carry, a result of this sum, carry of this addition is given as an input to input C into this addition. So all of these full addition will form the second layer. Now similarly a third layer would be there. You also notice that as a result of second layer we also have got, or we have also generated second bit, P2 bit of our result. So similarly the third layer of the fourth partial product, so multiplication of x3 with my multiplicand would be added in this particular layer. So here also, like our previous layer, like whatever now these vertical arrows represent, these vertical arrow represent the overall addition done so far, and the slanted or this tilted arrow represent the carry from the previous full adder. So all of them would be added in this stage, and this is the by now we have added 4 partial product with x0, product with x1, x2 and x3. Now in the next stage we would be adding the fourth or the last partial product to the final sum. So in this last partial product, you see x0 a4 is the input here, and whatever is the carry from the previous adder is given as a carry input. All the vertical lines are the sum from the previous layers. Okay, so you still see that x3 a4, the component which was left from the previous partial product, would be added as a vertical arrow as one of the input. Now what about the sum of these final ones? Now it's a last interesting case, the last stage, and also the most interesting one. Here this is like in Wallace tree multiplication, this is also a carry propagating stage. Here whatever result we are receiving here, so for example the result of this, because of space constraint we have to shift, make these arrows little more not so straight as they were here. So whatever is the carry of this stage is coming as a carry input of this. The sum is, this is essentially a vertical arrow, so this the sum from this stage is given as an input here. Now remember, see the carry which is carry out from this particular full adder is given as an input to the next one. Okay, so this is the carry in from this full adder, this is the sum from this adder, and the resulting carry is given as an input to the next full adder. Similarly here also resulting carry is given as an input to next full adder. x4 a4 is also given as an input to this final full adder. And you will also see that p4, p5, p6, p7, p8, p9. So p5, p6, p7, p8, p9. So these are also the final outcome of the last layer. So in this way, this looks like a very regular structure where we clearly know how many full adders would be required, what is going to be the delay of this particular adder, and how they would be connecting. So while designing, you can see, because the structure is so nice that I can create these partial additions and I can create n-1 stages of these partial additions. And finally this particular stage could be different, where we are propagating carry, where delay could be slightly different, but but this is also quite a regular structure. So this particular array multiplier or a combinational multiplier is more effective solution whenever a regularity is required. Here my overall hardware structure will also be sort of a rectangular or even a square structure, which is very layout friendly. What about area and delay? So here I can see clearly the delay is order of 2n. You can see It's not exactly 2n, but we can calculate from here the adder delay of this. The if we see the longest path or the most critical path here, you will see it is coming from here. This addition, so this is the longest path. This addition, then this addition, the output is going to this addition, and then output is going to this addition, then output is going to this adder, this output is going to this adder, this output is going to this adder, so on so forth. So the total number of full adders in my critical path is 2n minus 1. Total here it is 1 2 3 4 1 2 3 4. The total number is actually 8 here. So that means whenever whatever is the size, it's always going to be 2n minus 2. Why? Because the first bit we will always get from here, x0 a0, and the last bit, final bit, we will get as a carry of my final adder. So this way, whatever is, let's say the number of operands are n and m, that the delay is going to be n plus m minus 2. Okay. And similarly, if you see the area is also predictable. So here you can say in my initial stage is 4 4 4 4. So basically n minus 1 square, that would be the number of adders which would be required in adding partial products. And in final carry propagation stage, again n minus 1 number of adders would be required. So the total number of adders are of the order of n square. So this particular array multiplier also have some additional interesting properties, that I can easily divide this particular addition in two different stages. One, so here you see the delay of this particular wherever we are saving the carry, we are adding the partial products, we are not calculating the final sum. The delay of these 16 additions are equally good or equally same, equal to the delay of my last stage. So I can divide this adder into two different stages, one where I am adding the partial products, and the second one where I am propagating the carry and calculating the final sum. So this way, creating this multiplication as a two-stage multiplier also help in something called pipelining, which this pipelining we'll understand little later, but it would help us in breaking this multiplier into two different stages which are both almost equal in delay. So with this, we can almost close our multiplication methods. So there are many multiplication methods, but I have chosen these two so that we can understand some of these techniques which can be used for multiplication. Now, as a summary, we have seen in this lecture how to design efficient multipliers. We have seen two different methods. One is tree based method, where a tree of carry save adders was created, and finally a carry propagation layer would be required to add all of them, and the delay for that particular the number of stages there were around log n, and the delay was also the order of n. While we have also seen this very regular structure like array multiplier or a combinational multiplier. So in this combinational multiplier or array multiplier, the number of the delay is slightly more, but it is more a regular structure and can also be divided equally into two parts. So with this we can almost close this lecture, but let's ask one more question to ourselves, that when we have studied multiplication, binary multiplication, so at that time we have seen that if we multiply two n bit numbers, and both of these two bits, two n bit numbers are represented using 2's complement, then and result is also n bit result, then we can say that the result is always going to be correct. But in this particular exercise, in today's lecture, we have seen the result is of size 2n. So the question is whether this result of 2n will always give correct result in case of unsigned numbers as well as signed numbers. Answer is no. In case of unsigned number, it will always give correct results, but if we follow these techniques as is means that the way it has been described in this lecture, if we simply add those partial product in the same way, then signed number will not give correct results. There would be certain modification which is required. So I'm not going to discuss those modification in detail, but let's give a very quick intuition. So essentially, let us say my multiplicand was negative and multiplier was positive or negative, it doesn't matter. So if multiplicand was negative, each partial product, the first partial product, so let's consider 4 cross 4 multiplication. In case of 4 cross 4 multiplication, the first number after multiplying with the 0th bit of multiplier is a 4-bit number. So now this 4-bit number tell me whether this number is a positive number or a negative number. Since the result is of 8-bit and partial product is of 4-bit, what are the rest of the what are we going to assign to the rest of the bits? So because my multiplicand was negative, I have to sign extend each of these partial product. If I do sign extension of each of the partial product, then all of the techniques which we have discussed today will work in a same way. The only thing we have to do additionally is we have to have this sign bit or sign extension. We have to have additional full adders which will take care of this sign bit, which will take care of this which will do sign extension, and which will also the signs would also be added along the path. There won't be any impact on the delay. So for example, if we see this last one, so let's say there is another addition here, there is another addition here, so still the worst case path is going to be 2n. So there is no impact, at least on array multiplier there is going to be no impact if we have the additional adders in this lower half, in this upper half. Triangle also there would be half adders as full adders, and these full adders will create some additional results, and yeah, but the delay is going to be still same. Okay, so with this we can close today's lecture, and I'll say thank you very much.